Hello, everyone. I hope you've just enjoyed the wonderful talks covering various aspects of RTC video. Now, we are very happy to have all our speakers, Xiang, Thomas, Gan, Fengden, and Fan, join us live for the Q&A session to share their thoughts, experiences, and insights with us. My name is Ji Dang. I'm a software engineer with the video calling team here at Meta. I work on video call quality measurement and improvement across Meta's RTC products like Messenger, Instagram, and WhatsApp. And it's my pleasure today to moderate this Q&A session. Now I've seen the questions coming in, and we'll do our best to answer as many of them as possible. So let's get started. Xiang, I would like to start with you. Do you leverage SVC capabilities for AV1 in order to support relay architecture?
Oh, yeah, that's a great question. So the way we started was majority of our calls are one-on-one or peer-to-peer calls. They still go through relay server. So some of the SVC capabilities, they are more applicable for large group calls or group calls. Definitely like the simulcast will be applicable there. But temporal layer is something that we leverage even for peer-to-peer, and we are running experiments on that right now. So we are using some features like RPR of AV1 for peer-to-peer calls, and we are running active test on temporal layer, which we have been using in previous codecs with AV1. And in future, when we expand it to group calls, then we will be leveraging the features like simulcast and more advanced features.
Yeah, there's another question for you, Sham. How do you switch codecs on the fly without interruption to playback? What challenges did you face while implementing this?
Yeah, another great question. So the good thing is we have been using SDP as a signaling for negotiating the codecs, and it allows us to negotiate multiple codecs upfront. So for example, between all the participants, we can negotiate all the capable codecs and then find the intersection. In past, we have also been able to switch the codecs when some participant joins who is not able to support, let's say, a participant joins from a very old app version, which does not have the latest codec support. So in a normal case, we are able to negotiate, let's say, H.264, AV1, VP8, all the codecs at the beginning, at the call setup phase. And then during the runtime, we detect based on bit rates or CPU usage, the sender can make a decision to switch the codec from 264 to AV1 without any negotiation. The decision is on each frame basis. It does mean like the sender has to encode a new keyframe because it's a switch of the codec and start a new codec, which is same as any resolution changes, which we do for sender when the bitrate changes. And the same thing on the receiver side, the codec type or the payload type identifies what codec is associated with. And the receiver is able to detect that the input RTV packets have a change in the payload type, and they are able to instantiate the different codec and decode it. So what we measured was for the end users, it looks seamless. There is no glitch, there is no big pause, but still like there is hundreds of milliseconds of glitches in some cases depending on the jitter buffer and network sizes or the network conditions, but mostly it's seamless, like almost not visible to the end users.
Thanks, Xiang. So now I have a question related to the long-term reference frame. Does this repair scheme scale to middle boxes and relays for large SFU-based multi-party calls? It seems like that instead of placing the burden on relay node NAC buffers, the burden has to go back to the original sender to generate these LTR keyframes. Fan, would you like to share your thoughts on this?
Sure, that's a great question. So in fact, our current approach only works for the P2P immediate pass. So we're expecting to adding the support to the group call, the effort will be non-trivial. So first of all, it is true that this burden cannot be put on the relays. and the request has to go to the source, which actually have the buffer of the long-term reference frame, so that can generate LTRP based on the buffer of the LTR frames. So second of all, on the receiver side, so imagine in a large group core, it might receive the multiple streams, right, from all the other senders. In that case, when it only has one outgoing stream, then it need to acknowledge the LTR sent from like multiple streams. That is non-trivial. So that's why we haven't really considered expanding this to the large group core yet.
Thanks, Van. Here's another question for you. We configure video encoders to have a certain number of reference pictures. LTR may focus us to increase this number. This in turn would impact the encoder and decoder complexity in this shortcoming.
That's definitely a great question. So as a matter of fact, we don't really adding a lot of actual long-term, a lot of frames. So for example, the OpenX264 it only use at most one long-term reference frames. So which means that no matter how many long-term reference frames you might generate, so it will only generating the LTRP based on the most recent act LTR frames. The similar thing also applies to the hardware encoder as well. So as far as we know, the iOS hardware encoder only also can support at most 4 long-term reference frames, and also it can only use the latest acknowledged one to generate LTRP. So it doesn't really add a lot of complexity to the encoder and decoder design here.
Thanks, Fan. Now I have a question related to AV1 encoder. What do you think is the limit of performance for AV1 in RTC, especially at lower complexity? Thomas, would you like to share your thoughts on this one?
Oh, that's quite a hard one. I think it depends a lot on where you sit on the complexity spectrum. So on the complexity side, you can think of AV1 as a kind of superset of VP9 and a VP8. So you kind of know a priori that you can match the complexity and performance of those prior codecs. Most people don't write an encoder to do that, but it does mean that you should have confidence that you can do that. You can adjust your encoding algorithm to at least match the performance of prior codecs. But the more wiggle room you have, the more CPU you have, the more you can get coding gains out of that. So what's challenging in writing an encoder is not necessarily supporting very low complexity. It's supporting a big range of complexities. So it's possible to get very significant gains, as I hope I showed in the talk. But when you have an encoder that's capable of supporting these very high performance operating points, there can be a lot of overhead in your encoder in order to reach those lower complexity operating points. So you have to write things in a kind of scalable way to do that. So in quality terms, I think I've really been surprised at how much extra gain we've managed to get in recent years, both in the open source codecs and in our own. Really, there's a lot of mileage, and I'm excited by the possibilities of using really clever pre-analysis with increasing use of ML techniques. So I think the sky is the limit, really. There's a lot of mileage still to go, even in low complexity RTC encoding.
Thank you, Thomas. Great. Yeah, I personally also thought about a similar question, whether we can use the AV1 as H.264 if we trim the AV1 heavily enough. Appreciate your insights. So we have question. The next question is about the 360-degree video. So Gang, this question is for you. Why choose software video codecs when processing 8K 360 video?
Yeah, so that is the implementation decision, and at the moment we have this set up this implementation. Not a lot hardware codecs support 8K transcoding. The second factor is about this tailing and piking during the 360 video processing. So it is very important to have this the random access, especially on this 360 video encoding, so that we can quickly switch the viewport. So that kind of feature is supported in the HEVC MCTS, the motion constraint tail side. That is, however, that is not a kind of, it is just an extension of the HEVC standards. So it's not widely implemented in the hardware HEVC encoder. So that is the reason, finally, we can select the software HEVC encoder support the MCTS. Then we make this choice for the 360 video encoding. Certainly, if for now we have quite a lot tools in AV1 and also VVC, so it's likely to have a much better hardware acceleration for the AK 360-degree video encoding.
Thanks, Gang. Now I have another question related to long-term reference frame. Looks like the long-term reference frame is really popular topic. So, Fan, the quality of long-term reference frame depends on video content. For high motion content, the quality and the required rate of LTR could be worse than keyframe. Do you consider this to request LTR?
Yeah, that's a great point. So, in fact, as a matter of fact, the quality of LTIP highly depends on a lot of factors, such as video content and also the difference between the LTIP and its reference frame. As mentioned in this question here, so if there's a lot of, for example, motion in the video content and the difference between the LTIP and its reference frame is large enough, then in some cases we observe that most of the LTIP consists of only like eye blocks, which means there's not much difference between the quality size of LTIP and the keyframe. So we definitely will consider do some optimization here. So for example, we observe that we are aware that there's a mechanism to detecting the difference between the frame and its reference frame in the OpenH264. So definitely one optimization we can make is that if the difference is large enough, then we consider instead of generating another LTIP, we can fall back to a keyframe in that case.
Thanks, Fan. Yeah, LDR does not come for free, but we need more thoughts to handle them carefully. Fengden, here's a question for you. Is it possible for FEC layer to provide more bits for key LTR frames and less bits for rest of the frames to save bandwidth?
Yes, this is what's being done as part of WebRTC solution. It gives more traffic to protect keyframes, and we are adding support to give the more traffic to LTR frames, even for retransmission data as well. That turns out to be very useful.
Thanks, Fengden. Xiang, here's a question for the BWE part. For the higher bit rate, why did you have to make changes for the BWE that comes with the WebRTC?
Okay, yeah, I think so. The default bandwidth estimation and the Google congestion control that ships with WebRTC does an extremely good job for most of the use cases for RTC, right? But when it comes to really increasing the bit rates and pushing the networks to the limits, there is scope for improvements. And BWE is still an area which is still evolving, right? There is no fixed algorithm or a single algorithm which is considered as an industry standard or this is like solved problem. So this is where most products they differentiate. And to some extent, the design of algorithm depends on several factors like what scenarios your product supports, what your customer base is, in what conditions they operate, and what you are trying to optimize for. Is it for the video quality, audio quality, or enterprise or consumer? So this is an area where most products innovate and differentiate. So every product has their own secret sauce, and this is what we also did. And the analogy I would make is the algorithm works for a certain conditions, but when you increase the bit rates, you have to keep evolving it. So for example, consider, let's say you are building a car, right? And you have a really good engine. Now you can easily press the gas and accelerator to go to the higher speeds, but you can't simply keep on increasing the speeds or engine unless you keep evolving, like let's say the tires and the brakes, to be able to handle the congestions on the road or slippery conditions. So you have to keep evolving both how you push the network limits or how you increase the video quality and bandwidth, and also keep evolving your bandwidth estimation and congestion detection algorithms to avoid those really bad congestions and call drops.
Yeah, interesting. The speeding could be terribly dangerous without the premium tires and brakes. Again, let's look at another long-term reference frame. Is there a way for Pacer to control the number of frames between keyframes? Fan, please.
Yeah, we actually don't control that from Pacer. So there are a number of other ways we can control when do we want to send keyframes, right? So for example, we used to have a control on the encoder side that generated keyframes regularly, maybe something around every 2 seconds. But we found that it doesn't really bring any benefit. Right? It doesn't really bring benefit as keyframe usually have large size and less quality than ordinary keyframe. So as of now, we don't really sending proactive keyframes, and all keyframes are sending on demand way, right? So for example, we have resolution change. In that case, we have to send a keyframe. Or when the decoder is getting blocked, then the decoder needs to request a keyframe to have a fresh start. So now, yeah, we have way to control when do we send a keyframe, but we don't send a proactive keyframe and proactive keyframe, and we don't control that in Pacer.
Thanks, Fan. So now I see a question regarding the screen content for the AV1, which I am personally very interested in it. So AV1 seems to give really good results for screen content. What's the reason for that? Are there types of content that are especially challenging? Thomas, would you like to address this one?
Yeah, I mean that's a really good question. I think people have alluded to that, the fact that AV1 has got screen content tools in the main profile, and that's obviously really useful, but actually that's only part of the story. When you're targeting an encoder on screen content, the content itself behaves differently to camera content. So being able to deploy those tools with encoder algorithms that understand the statistics of how those frames and, for example, scrolling video and the kind of content that you have with Word documents, Excel spreadsheets, web pages, that kind of thing. That's also really important. So you've got to have an optimized encoding path for it as well, and put the two together. What's really challenging in RTC is when you have mixture of content where there's very different statistics put together. So if you think of an example of sharing a web page with embedded videos in that web page, so you're scrolling up and down and videos are playing inside that web page, that can be particularly difficult because you're trying to optimize for motion in some parts of it and optimize for screen content in the other. So that's something that I've spent some time on in my life doing that kind of thing.
Thank you, Thomas, for sharing your insights on the screen content coding tools. So there's another question from the audience. What's the most challenging part to build an end-to-end XR application? Gang, would you like to share your insights on this one?
Yeah, I think this to build an end-to-end solution, we often need this kind of cross-domain collaborations. So basically, you need components from the media industry and also from the network industry and from the technical wireless industry. So what we kind of experienced is in each industry, there are quite many valuable and legacy technologies. But very often we see those innovations from one industry may not be quickly adopted by another industry. So that makes this kind of coordinated evolution very difficult. For example, the video codecs AV1, it is if we want to really kind of promote the AV1 codec in the telco industry, that takes quite a long time to do that. The second thing is about the interoperability. So basically, if we want to have an end-to-end solution, we had to consider the device and also the users across regions. So that means many components and technology need to be standardized and synchronized.
Thanks, Gang. So we are close to the end of the Q&A session, and we have time for 2 more questions. So Fengdeng, here's a question for you. What causes the extra FEC header overhead for Reed-Solomon code when compared to XOR FEC?
Sure. So the RS code decode requires the encoding group information to get the correct decoding matrix. Versus in XOR FEC, you just need to know what are the packets that used to protect, that used to generate this FEC packets, and then you just need to grab this FEC packets and fill the gap for the lost packet. So that creates a little bit more overhead for RS code payload header.
Thanks, Fengdeng. So the last question, that's end the session by the long-term reference frame. Fan, so the question is, from which codecs are you seeing the improvement by using the long-term reference frame other than H.264? Also, is Meta team planning to make upstream contribution of long-term reference frame to the WebRTC community?
Yeah, that's a great question. So as of now, we are only applying it to H.264, both software and hardware. So we have already shipped this long-term reference frame on the software encoder across the Messenger app. But as far as I know, the WhatsApp team is also successfully applying the LTR to VP8 as well. And as for the contribution, yes, we are actively considering doing that. So as a matter of fact, we've already started some discussion with upstream and other company on how the upstream part of the design in the upstream community.
Thanks, Van. So, well, it is toward the end of the session, and there are still questions from the audience we're not able to cover here, but we will make sure that questions are all answered offline. Again, I would like to thank all our speakers for the great talks and taking the time to share their experiences with us. And I also want to thank our audience for their interesting and engaging questions. Thanks, everyone, and see you after the break.